to show me. I do like to see signs of life. Um, okay, what I'd like to talk about today is I'd like to do a daily problem on graph algorithms. That is, it's kind of a hard one, but if you understand it, I'm going to try to do it two different ways. And if you understand these two different ways, think about them actually as kind of looking ahead to later in the semester, because there's going to be there's going to be one way of looking at this problem that is going to look like dynamic programming, which is what we're going to be doing after probably starting in about a week and a half or so, maybe a week or so. Then there is something that's related to like an NP completeness reduction, if you see it in the right way. Okay, but it has to do with finding graph algorithms for an algorithm for solving the following weighted graph problem on a weighted graph. You're given a directed weighted graph such that all the weights are positive. You're given two vertices in the graph and an integer k, okay? And you want to find the shortest path from U to V in a graph that contains exactly k edges. Okay, and note that the graph path need not be simple. That's what the problem is. Are these slides smaller than usual? People don't like seeing the slides, or okay, let me do something then. That's interesting. I appreciate the feedback. Is this better? Who here thinks this is better? That is amazing to me that actually is better. That just so you know, kind of when I put the view in the Zoom, it amazes me that the window that I'm seeing it is actually what's changing this. But that's beside the point. Okay. Okay. So what is an example? Let's just see if I can come up with an example here of what I kind of want to do. Let's say I've got a directed graph that looks like this. Let's say it's 1, 2, 3, 4. Let's say the vertices are A, B, C, D. And let's say that I want to find the shortest path. Let's just see if I can figure it out. You see how the edges, it looks like I have, this is directed, it goes like this. Suppose I want to find the shortest path. Let me make this middle edge cost 10. What is the shortest path from A to D? The distance from A to D using exactly two edges. What is the shortest path length from A to D using exactly two edges? Somebody. 11, right? Now, what is the actual shortest path from A to from A to D?
4.
4. Okay. Not A to D is not 4 because this edge is going like this. A to D should be 6, right? 1, 2, 3, 4. A to D.
Oh, sorry.
In 4 edges, the shortest path should be 6. In 2 edges, okay, it would be what did I say? 11. What's the length of the shortest path from A to D using 5 edges? Does anybody have an idea? Is there a way to do it? 1, 2, 3, 4, 5. I claim that there is a way to get from A to D in 5 edges, right? It would be A to B to D to A to B to D. Is that the cheapest way to get there in 5 edges? I don't think there's any other way to do it. Is there? Okay, so A to D to, and what would that be? That would have been 11 plus, what you call it, 15, if I am correct. Is that 26? People see what I mean if I go bunk, 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 bunk? Okay. So, okay. So my question for you now is, if I give you a pair of vertices and I give you a number of edges you need to do, can you find the shortest path from A to from U to V, U to W, using exactly K edges? Can anybody come up with a way of doing it? First of all, suppose I don't. I want you to know if there is a path. What if I want to find the shortest path from A to V, U to V? How would I do it? If I just want the shortest path, what's the answer?
I mean, you could use like Dijkstra's algorithm with.
Okay. Now, what if I want to know if there's a path involving exactly K edges?
Floyd-Warshall.
What?
Wouldn't you use like Floyd-Warshall for that?
Well, Floyd-Warshall, remember, this is allowing cycles, okay? And I certainly, it's funny that the answer is no, but for Floyd-Warshall, remember, was counting. The key idea was what was the shortest path from I to J using 1 through K as possible intermediates, right? That was the idea. What vertices you were allowed to use in between. You could use them as many times. Okay. One possibility is finding all paths of length K. Okay. Now, if I wanted to find, that's something that backtracking, which is what I'm going to try to talk about today, is actually good at. Okay. So I wanted to go through, one possibility is do an exhaustive search for all paths of length K. And backtracking that I will show you today is a good way to do it. And you could find the smallest of them, and that would be correct. But that actually would be exponential, as you'll see, I think, when we start talking about backtracking. Okay? But how can we find what is the one that is exactly K edges long, the shortest path? And one idea was using, I heard the word Floyd-Warshall. That meant that there was a recursion, but you really meant to say Floyd's algorithm. And you meant to have a recursion to do it. And what I am going to do is, let's say that D sub X, comma Y, comma K is defined as the length of the shortest path. Can you see this, right? Path from X to Y using exactly K edges. If I could compute this, this is exactly the answer that I'm looking for, correct? Now, can anyone give me an idea at a recurrence relation that might tell me what this is to compute this thing, a recursive equation? We haven't really done this yet, so if you can't see it, I don't want you to think, but let's just see. Can anybody get a whiff of a recurrence relation of what the shortest path from I to X to Y would be that used exactly K edges? What the length of that would be? Okay. I am going to say it is the min over all Y. No, not Y. Let's call it Z. I want a new variable. Of the distance from X to Z using K minus 1 edges plus the weight of what you call the last edge, which goes from Z to Y. Look at this for a second. Okay? Does everybody kind of see this thing? Okay, so maybe I'm seeing something here. Actually, I'm going to move this just because it's blocking my screen, which I had to enlarge so you guys could see what you wanted to see. Do you see what this equation is? Do you see that the shortest path from x to y of length k is going to have a last edge? And what is that last edge? It goes from some vertex z to y, doesn't it? Has to end on y. The weight of the last edge is the weight of that last edge. The cheapest way to get from x to y using k edges is the cheapest way is for some, whatever the desired last vertex is for z, it's the cheapest way to get from x to y, x to z in k minus 1 edges, plus the weight of getting from z to y. Does everybody see that once I have figured out what that vertex is, which z it is, this has to be the cheapest path overall. And I'm going to try all possible z's to make sure this works. How do people sort of see this? Do people see why this kind of recurrence relation gives us the right costs? Or any questions or discussions I'm delighted to have.
Question.
Yeah,
If you did that, wouldn't you need to have like a recursive base case where k has a length of 1?
Okay, so you're right. I need a basis case. What's my basis case? Does anybody have want to propose to me what a basis case is?
The distance between x and
I'm hearing if k equals 0, one possibility, if I did it for k equals 0, what is the distance from x to y using 0 edges? What does that matrix look like? Can you figure that out? If you're not allowed to use any edges, what's the distance from x to y?
infinite?
Infinite? What if x is equal to y? You're not using any edges. If you know, what's the shortest path from me to this chair in my office using 0 moves?
Well, it depends.
I'm here.
If there's an edge which circles back on itself, then that weight is defined.
Okay, well, walking on a self loop, I would argue, is walking on an edge. If you're telling me what's the shortest path, the length of the shortest path from me to you where you're not allowed to move at all. Well, if I'm at the same, I think of this as if I'm at the same spot, it costs me nothing to move. If I'm not allowed to use any edges, it's infinite cost to travel between any two places. There's no way I can get there, right? So I would set this to be equal to the basis case of being equal to 0. If you want to say, I don't like that, I want to set it to be equal to 1, what would the basis case be if k was equal to 1?
the minimum edge weight for any edge that includes x in it.
You're only allowed to walk over one edge in getting from I to j. So what's it going to be? It's going to be the weight of an edge from I to j if there is one, and infinite if not. Does everybody kind of see that? If I am demanding, let's say you want to go from A to C in one edge, you're only allowed to walk on one edge. What's the cost of getting from A to C in one edge on that graph? Can anyone describe me how to do that? Infinite, infinite, okay? So I think, yes, you do need a basis case. Does everybody see that we kind of know the answer when k is small enough? 0 or 1, we're pretty good at telling the answer. And this gives us a way of doing it for now arbitrary k. Does everybody see that? Any questions about this? No.
Yeah, so out of curiosity, since we can have edges that circle back on themselves,
Yeah.
and we're going to have situations where, say, the shortest path is going to involve a edge which loops back on itself potentially several times before then moving on.
Right.
Does this handle that? Because I don't
Yeah,
feel
I don't
like it's
see
not
any
immediately
reason
obvious.
why it doesn't handle that. Let's say I'm now adding a what's the cost of staying on B? There's a self loop I just added around B, right? Well, how much you want that cost to be every time I walk on it?
I don't know, 1.
1, okay. Now, what is a path of length 3 that gets from A to B? It'd be 1, 2, 3, right? The last edge on the door would be the cost of weight from B to B. Z would be equal, if this was Y would be B, Z would be B. The weight of Z to B would be 1. We know that if we're going to use the self loop as the last edge, we're then interested in, is there what's the cheapest path from A to B using 2 edges? And the cheapest path of that type is going to use a self loop again. Okay, so there's no reason why that would bother me. Self loops are a perfectly good thing. Okay, but if they're in the graph, this method would work just fine. Thank you. Any questions about that? Do people kind of see this? Okay. Any questions? Now, the $64 question is, what is the running time of this algorithm on a graph with n vertices? Okay. Now, how many times, if we're going to do this recursively, if we're going to fill in this table, if you think about it, is something like n choices for the first vertex by n choices for the second vertex, and k possibilities for the next thing, right? Okay. And to fill in each one of these cells, I had to figure out which of the n vertices to try, and then look this thing up in a table and look this edge up in a table. To compute any one of these things, I've got to iterate through all vertices from 1 to n. I claim, if you see this the way that I'm seeing it, this is going to mean that there are n times n squared k cells, each of which took n time to fill in. This would actually be an order n cubed k algorithm, the way I have done it now. Okay? Any questions about that?
Yeah,
Okay.
could you say where you're getting each of those n's and k's from again?
Well, how many choices got this matrix that I'm filling in, right? So with the matrix that I've got, this matrix is going to be, it's an n by, graph has n vertices, so the number of starting points is n, the number of ending points is n. The third parameter was the length of my path, which is k, right? It started out as k, and we're going to make it smaller with time. So my claim is that this recursive function has at most n times k interesting values. Different arguments, sets of arguments that you're calling it on. And to fill it in when you need it, you're finding the minimum of n possibilities. So one way to think about it is that you've got n squared times k boxes to fill. And each box takes at most n steps to fill. That's why I got n cubed times k. Any questions?
Yeah, gotcha.
Okay, this is not the trivialist example. So if you kind of are following this, that's good. Okay? Try to practice this and look at this again, because when you get the dynamic programming, many people seize up, okay, and they can't see what's going on. Okay, if you can see what I'm doing now, you will be a happier person about a week from now. Okay, so I encourage you to look at that. Any questions about this? Let me show you one other crazy way to do this problem, which I kind of like, okay, which is just to show you another kind of strange way to think about it. I guess our graph looked something like this, if I remember correct. Is that right? That was kind of what our graph looked like, okay? A path not being simple means that you can repeat vertices. What if I want to find the shortest path from A to C using exactly, A to D using exactly 3 edges? Let me show you a way to do it. What if I built a graph by making 4 copies of the vertices? Everybody see how I made 4 copies of the vertices? This is going to be copy 0, 1, 2, and 3. Does everybody kind of get that? Now, suppose I run my edges from each copy to the copy below it. Okay, so the edges on the first one should go from what? This edge should go from A to B. This edge should go from B to C. This edge should go from B to D. This edge should go from C to D. Then there should have been an edge from D to A. Does everybody kind of see what I did? All my edges are now going down to the next level. Does everybody see that? Building me a new graph. Now suppose I do it again to the next level. What would this look like? Okay, I'm going to have an edge from A, goes by definition to B. Sorry about that. Now delete. Let's try it. A goes to the B. B goes to C. C goes to what? D. Okay. D goes to A. Right. And there's also, I guess, another one that B also goes to D. Right. I think those are the edges I wanted to add. Does everybody kind of see what I did? Does everybody see I could do it one more time? I'll even add another color. Kind of in that kind of mood. A goes to B. B goes to C and D. Okay. C goes to D, which I think is that. And what was the other edge I needed? I guess D goes to A. Does everybody see this? I've built a new graph like this, right? Now I claim the shortest path from A to D involving exactly 3 edges is going to be the shortest path from here to here. Is there a path of length 3? Ka-chunk, ka-chunk, ka-chunk. There is a path of length 3 in the original graph. Does everybody see that that path, all these edges are directed, right? All these edges go down. What do we know about the graph I created? Does it have any cycles in it? Let's think about it. Or is this a DAG? Let's think about it. I see no's. Is this a DAG? Is this a directed acyclic graph? How do we know there's no cycles in it? Well, every edge goes from stage I to stage I plus 1, right? All the edges are looking ahead. right? Okay. Now, does everybody see that if there is a path of length 3, I'm going to be taking one edge in the first step, ka-chunk, one edge in the second step, ka-chunk, one edge in the third step, ka-chunk, right? And each edge is stepping down to another layer. Does everybody see that any path of length 3 in the original graph is a path of length 3 in this graph, right? And it's not a, and there's no cycles in it. There's no simplicity issues. I could spin around, you know, if there is a cycle of length 3 from A to A, but that would simply be the path from this vertex to that vertex, okay? So what am I saying now? If you understood what I just did, if you took this graph, transformed it into this graph, does everybody see that running Dijkstra's algorithm from this vertex to this vertex on this graph solves our problem? The shortest path on this K-stage graph is exactly the shortest path of length K edges on the original graph. How many people see that? That it's really, if you've seen this transformation I've done, does everybody see that I built a new graph? And, okay, now I can use Dijkstra on my new graph, okay, to solve my old problem. Any questions about that? How many people see that, don't see it?
Yeah, how would we analyze the runtime of this?
So
Because
what
running
is the running
Dijkstra's
time of
algorithm,
this thing? That's a
it
good
seems
question.
like it wouldn't be any different than normal Dijkstra's algorithm, just
Well,
because
it
we're
wouldn't be
multiplying
any
the number
different
of.
than normal Dijkstra's algorithm because it's normal Dijkstra's algorithm. But
Yes,
you've
and
got to
the
be
number of
careful about
nodes
the
is
fact that
multiplied by
you've got a
constant.
graph here that is a different size than your original graph, right? The original graph had n vertices and m edges. How many vertices does my new graph have? Can anyone tell me how many vertices my thing has?
K times
KM.
n.
I am seeing k, I'm going to do k times n, right? If I knew what k was, I made k copies, ka-chunk, 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 right? How many edges did I have? I think I made something like k times m copies. Isn't that right? Now, running Dijkstra on a graph with this size is the running time of my algorithm, right? Assuming I made my graph efficiently. So if I took linear time to make this graph, okay? What is the running time? Well, Dijkstra's algorithm, as I called, when we were running Dijkstra's algorithm, it was order n squared. Isn't that right? In our garden variety Dijkstra's algorithm, that would have meant that on the new thing, it would have taken k squared n squared time. Does everybody see that? Okay. This is an example of an idea called a reduction. I took my hard graph algorithm problem, I didn't know how to do it, and I translated the input into the input for another problem I knew how to do. That was shortest path, right? Dijkstra was a smart guy. He knew how to do shortest paths. If I can convert my problem to a shortest path problem, I don't even have to know how Dijkstra's algorithm works. I can call it as a black box and it solves my problem. Any questions about that? Do people kind of see this approach? Okay, these are two different clever approaches. We will see reductions when we talk about NP completeness at the end of the semester. Okay, and we will see these kind of dynamic programs about a week from now. Any questions about that? Either of these approaches or algorithms or ideas? Okay. I want you to think, because if you see that why this is working, they're kind of cool ideas, okay? You will then be able to understand what I'm doing later. Okay? Any questions? Is reduction similar to, no, reduction has nothing to do with, reduction has to do with reduction. Transformation. A reduction is a transformation from one problem to another. And that I don't think of in terms of, so that's the kind of flavor that I'm looking for here. Any questions?
If you don't mind, could you just go over really quickly how you converted the first graph to the second one, like why you needed to do that in order to solve it?
Well, why did I need to do this? Let's think about it. The original problem was find me the shortest path of length k, right? In k edges. Does Dijkstra's algorithm know anything about k edges? It knows about the cheapest way to get to a vertex where, you know, where you're not allowed to repeat vertices because that's not going to find you a shorter path. Okay? So we needed to do something to help kind of memorize where we are. What is k when you've got something? What can you reach in 1? What can you reach in 2? What can you reach in 3? Right? That was the idea here. Okay? Coming up with this idea was clever. Okay? So maybe you're not so clever yet. Okay? But you should be able to understand it once you see it. Right? That's what I'm kind of hoping. That you kind of get the idea. We're remembering how many edges have we used. And we're basically keeping track, if you think about it. The shortest path from here to here is the shortest path to get from this vertex to that vertex in 2 hops. That is, if you think about it, kind of like what I was storing up here. Right? Okay. Any questions about it? Any questions about either of these? Okay. For law, which one is better? Now, this is order k squared n. The other one is order, what did we say it was? The other one was n cubed k. Okay, which one is better? Well, if k was incredibly large, this one would be better. Okay? Suppose I want to find the shortest path from I to j using m squared edges, n squared edges. Okay? I'm really going to repeat a lot of vertices and stuff like that, right? If k was n squared, this would be n to the 5th. The other one, if k was n squared, this would be n squared squared, which is n to the 4th times n squared. This would be n to the 6th. Okay? So for a super huge one, this one would be slower than the other one. Okay.
Well, Professor,
yes.
Wouldn't we run into the issue as well of having an enormous km squared matrix that may or may not be able to fit in memory?
Okay, you're telling me, oh, I've got this matrix I'm keeping. Who said anything about putting it in a matrix? Couldn't this be, why wouldn't I have built this graph so that it was an adjacency list?
Not the graph. I meant with respect to when we're comparing this algorithm with the last algorithm, the dynamic programming one.
Okay, you're unhappy about the fact that I'm keeping a total of k of these matrices, each of which is n squared. You are worried about space, okay? That's not a terrible thing to be thinking about, okay? Turns out I may not, and that's something you could use. The truth is, if you're being a little bit clever about this, you can get away with less space, okay? One thing is, do I need to keep all k of these matrices around? Or once I've computed the second one, do I need the first one anymore? Maybe I can reuse the memory that I'm using conceptually for these matrices, okay? This is more than I think I want to deal with, but the short answer is memory, worrying about memory, smart thing to do. Memory can kill you, okay? But if you're clever, there's ways to get away with less memory than was explicitly used here. And that's where I want to leave it, okay? So don't let those kind of details confuse you at this point. The important thing to see here is there's two different ways. One by writing a recurrence of dynamic programming. One by constructing a new graph and using an old problem we know about. Okay, that would be doing a reduction, and both of them work for this interesting problem. Any questions? Okay, you got that? You'll be a happier person later on. Okay, any questions? Okay, so what I'd like to talk about now is one of my, a subject I really like, which is on exhaustive search, okay, backtracking. And many of you, I trust, have seen this thing before. This is a board of Sudoku. What is Sudoku? Has everybody played Sudoku, or is this now an ancient game? Who here, not if you're on the camera, have you played Sudoku before? No, okay. Really? Okay, I'm hearing some yeses. I'm playing. Some of your colleagues are doing it. Seems that if you're on the camera, you're the kind of person that doesn't play Sudoku. It doesn't make you a bad person. Okay, but what is Sudoku? It is a puzzle where you've given a partial grid of numbers and you have to fill in the rest of the numbers so that every row contains the digits 1 through 9 exactly once. Every column contains the numbers 1 through 9 exactly once. And every box contains the numbers 1 through 9 exactly once. The thing on the right is a Sudoku solution. This box, each box, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, bingo. This row, what does it contain? 1, 2, 3, 4, 5, 6, 7, 8, 9. This column, well, this column here, what does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And the puzzle is I give you a partially filled out Sudoku board, and your job is to fill the numbers in. Okay? And this is, I think, at one point was a puzzle that was sweeping the world. Maybe I'm showing my age. Okay. I bet you guys are even going to tell me the Beatles aren't popular anymore. Okay. So maybe I'm showing my age. Okay. But for those of you who play Sudoku, how do you go about finding a solution to this puzzle? Is there any Sudoku player who will reveal their secrets? Okay. Anybody? I'm hearing brute force. How do you do it? What do you do when you're confronted with a Sudoku board? Someone want to describe to me what you do? Preferably with a voice.
I think you could sort of iterate through like every sort of possibility, but with backtracking, I think the way that you're saying is that eventually when you're going through a certain combination, you know that if I go any further from here, it's a waste of time. So you just
okay. So we agree that trying there's a huge number of possible ways you could fill in the numbers. A dumb thing would be to try to draw every possible way of filling the numbers, and and then if it isn't a Sudoku solution, go to the next one. Okay. Instead, what people are saying that is basically true is you look for a square that is most constrained. Like, where would be a square that you probably know something about what its value is? What are the possible choices for this cell? It can't be a 1. It can be a 2. So a 1's out. A 2 is possible. It can't be a 3 because that's in the same row. Can't be a 4. I think I said it can't be a 3, right? 5, can it be a 5? See no reason why not. Can it be a 6? Okay, it can't be a 6. It can't be a 7 because it's in the same row. It can be an 8 or it can be a 9. Does everybody see that there are only 4 possibilities here? What you like to do is to find the place where it's most constrained, put that number in there, and maybe try these possibilities, and then look forward for other kind of constraints. What makes Sudoku fun is this idea that if you see it the right way, what is the most constrained number here? That didn't look like it. What about this one? This one maybe looks even better, right? Could this one be a 1? My Sudoku players of the world. This square over here, what could it be? Could it be a 1? No, because it's in the same box. Could it be a 2? No, because it's in the same box. Could it be a 3? No, because it's in the same row and column. Could it be a 4? Yes, it could be a 4. Could it be a 5? Can't be a 5 because it's in the same row. Could it be a 6? Can't be a 6. Could it be a 7? It can't be a 7. Could it be an 8? Can't be an 8 because it's in the same row, right? Could it be a 9? Okay, this one I've only got 2 choices for. Okay, this seems like a better place to be starting on. Okay, and for those of you who have never played Sudoku before, I encourage you for homework to go, do a little Sudoku. Okay, it's good for the soul. Any questions? Okay, so what's important is that in solving Sudoku puzzles, you're doing some kind of exhaustive search. Okay, but you're doing it in a clever way so you don't look any harder. Okay, you do as little work as possible. And backtracking is an algorithm for doing exhaustive search while doing as little work as possible. Okay, we're not going to end up with polynomial time algorithms. We're not going to end up with big O type analyses here that matter. But we are interested in programs that find the best possible solution as effectively as possible in practice. Okay, and this is a useful skill. Okay, any questions? So what is the idea of backtracking? Backtracking, we are going to represent our solution by a vector. Okay, a vector is going to tell us where a sub I, we're going to pick up our solution one element at a time. Okay, in the case of Sudoku, you put a number down. That's going to be the first. A number in a position is the first thing you put down. Then there is a number in the second position, which you will know basically will have some possibilities based on what you did for the first one. We're going to fill in this vector from left to right with what we have done. Okay, and this vector might represent the ith element of a permutation, might be A of I, or it might be something else. But we're building up a solution one by sticking elements in here. So long as we can make it longer and still get a solution, we do so. When we can't anymore, we backtrack. We take out the last thing and we go back here and try to find somebody else to put in there. Okay, any questions?
In the previous slide, you mentioned that you were looking for the most constraint number and trying to go for that first, right? But what I'm thinking is that if you were sort of programming this, or if you were going through all the combinations, it wouldn't really matter which index you worked with first, right? Because
the answer is not right. Okay, why is that? Because it depends upon whether you will eventually get there by filling in the most unconstrained thing. But if you fill in but it can require a vast amount more work because you're doing something where you have no clue, right? Why is it that people like to play Sudoku? They think they've got an idea, a thought process. Yeah, if I put it in here, I'm going to make progress. If you're just randomly putting numbers in, almost certainly it's wrong. You will explore a lot of non-solutions before you stumble across the right one. Whereas if you follow a disciplined kind of best first type strategy, you're more likely to find it, okay? Not necessarily. So that's why you might make mistakes and have to backtrack. But the hope is that if you pursue it in the right way, you're not going to get into trouble. Any questions? Okay. So what is backtracking? Okay. Basically, we're going to build a solution vector one by one. And what we're going to do is repeatedly, we're going to test whether what we have so far is a solution. If it is, we're done. If not, we have to decide whether we can extend it. If we can extend it, let's try to make it bigger. If not, let's say we can't, we've hit a dead end and we've got to recur, meaning we backtrack. Okay, we got to backtrack. We delete the last element and try again. That's kind of the backtrack part of it. Okay, let me show you an implementation. Let me show you a pseudocode and then show you the implementation. Okay, say backtracking is more intelligent brute force. It is brute force, okay, in an intelligent kind of way. Okay, and so what is the idea of backtracking? Here's the pseudocode. I'm going to be filling my solution, and let's say I filled in k spots so far, the first k elements of my solution vector. I'm going to test, is this already a solution that you want? If so, great, do something with it. Print it, send it to your mom, whatever you're going to do with the solution. If not, let's extend the solution. Let's make it bigger. Okay, k goes to k plus 1. We're going to now look at the next spot of the cell. And we compute all possible values for the next position, which are consistent with it. Remember, like we saw with that Sudoku thing, in one spot there were 4 numbers that were consistent with it. In another spot there were 2, right? We construct a complete set of candidates, and then one by one, try them in this the new k plus first position. If, okay, once we put it in there, we're going to backtrack from the new position. Now we have a bigger solution. Maybe it is a partial solution. Maybe it is a real solution. We're going to go recur and look at all things that have this as a prefix. Once if we come back and we didn't find something, well, then we're going to go through another candidate, okay, and try that. We're going to keep going through till we've tried all candidates from this position. If none of the candidates from here led to a solution, then that's a problem. And we bomb out of this recursion, which brings us back to an earlier level, okay? And that is kind of the motion that's happening in backtracking. You have to know something about, this is one of these things you have to understand how recursion is in order to make it work. Any questions? Now, if you understood, we also used recursion for depth first search. Remember, in depth first search, what did we do? Whenever we found a new vertex, we kept track of where we were, but started exploring deeper from there. That is exactly what we're doing, in some sense, on backtracking. If you picture there's a network, a graph of possible partial solutions, okay? Backtracking is how we are exploring those partial solutions, okay? If we do a depth first search in some sense through the space, we will eventually find the target state that we want, okay? Because we're going to visit all states, okay? And so backtracking and depth first search turn out to be very much the same. And if our network consisted of all vertices, of all subsets of a number or all permutations, okay, that's one way we can go through them, okay? Any questions? Okay, so later on, think whether you see why this is. You don't yet really understand backtracking. This is the backtracking algorithm implemented in C. Okay, you are going to have to use a backtracking to solve the next homework problem. Okay, that's our backtracking challenge. Okay, this is backtracking, the entire code. Okay, how do we find the optimal solution to my problem? Well, I'm going to keep track of a set of possible candidates. That's what that data structure is. Okay, I have a prefix here of my solution vector A. The first k elements are what I care about. I'm going to say, is what I have so far a complete solution to my problem? If it is, do what you want with that solution. Okay, if it's not, let's extend it. K goes to k plus 1. Give me all candidates for the k plus 1 position, given what I have in the first k positions, and store them in these candidates arrays. That's what this is about. Then, for every one of my candidates, try it for size in the kth slot of my solution. Forget about make, move, and this thing. These are actually only useful in some cases. I am now going to look ahead, backtrack, call myself recursively, okay, and wait till I got back. If I set a flag elsewhere saying that I had found my solution, then I'm done, okay? If not, keep repeating, loop around this, and if I can't, give up and go back to an earlier place in the recursive thing. Any questions? Okay. Do people see how this smells a little bit like DFS? DFS also was a recursive thing. See this here? Backtrack, backtrack. And it is kind of in a loop of all the possibilities. Okay, this smells a lot like DFS. Any questions? Okay, to make backtrack do what you want, you've got to make it, you've got 3 stubs to fill in, okay, that are important. One is called is a solution. Given the prefix, I've got my solution vector A, the first k elements, is true or false, is this what I was looking for? Okay, if it was, say yes. If not, say no. Input is just some auxiliary data that might be helpful to make it easier to tell if what I've got is a partial solution. Any questions? A second routine that I need is something called construct candidates. What does that do? That says that I am given a the partial solution I have, any other auxiliary input I need, and I'm given output arguments of an array of candidates and how many of them there are. This routine will say, what are the possible slots for the kth position given what I am given here? Okay? Any questions? This is like saying for the Sudoku board, for this slot on the Sudoku board, what are the possible values that could fit in here that are consistent with my rows and columns and boxes? And the final stub you need to write is something called process solution, which once you have a solution that's complete and beautiful, do whatever you wanted with it. There was a reason why you were trying to find the solution to this. Okay, maybe you wanted to print it out. This is a routine that you call to basically do what you want. Sometimes you want to count all the solutions. Maybe you just bop a counter up. Any questions? Okay. Any questions so far? Okay. So I want you guys, look, first, as our first backtracking problem, we're going to want to construct all subsets of n things. And to incentivize you for this, I'll tell you that your next homework problem, in some sense, is constructing, let me make sure I'm saying that true. Actually, no, I'm not saying that, but that's fine. Okay, never mind that. Okay. How many subsets are there of n things? If I give you the subset numbers 1, 2, and 3, how many subsets are there of 3 things? Somebody. Okay, this seems like a challenge. If I have the number 1, how many subsets can be formed from one element? I'm hearing 2. That could be, I could have the subset with 1 or the subset that is empty. Does everybody agree? Now, how many subsets are there of 3 items? Of the items 1, 2, and 3? How many possible items are there? Subsets are there? Okay, I'm hearing 2 to the 3 or 8. Why is it 2 to the 3 or 8? Okay, it's right, but why is that? I want to say it's because any subset either includes this one or doesn't, includes this one or doesn't, and includes this one or doesn't. Does everybody kind of see that? So there are 2 to the 3 possible bit patterns that correspond to each subset. Does everybody agree that I could represent a subset by a bit pattern? What subset of 4 items, if I have 4 items, what subset corresponds to the bit pattern true, false, false, true? What subset of the item numbers 1 through 4 corresponds to that bit pattern?
1, 4.
1, 4. Does everybody kind of see that? So what we would like to do is to generate all possible bit patterns of true and false. Does everybody kind of see that? And what I want to say here is that what we have to find all subsets, the candidates for the kth position in our solution are either true or false, and we have a complete subset if and only if our k is equal to n, meaning we have filled in the entire array with trues and falses. Any questions about that? Let me show you an example. What should be, if we want to construct all subsets of 1, 2, and 3, what should we be trying to do? We have a solution vector A. What are the choices for the first spot? Does anybody want to tell me what my choices of the first spot are? I like my voice now. Don't type it. Someone yelling. What are my choices for the first spot? Someone who has their thing on. What are the choices? Could either be a true or a false, right? Let's say I put in a true. Now I've used that candidate. What are my choices for the second spot? Does anybody have an idea? What choices can I have for the second spot in my solution?
True or false?
What?
You could do either true or false.
True or false? Maybe I'll put in the true first. Do I have a complete solution of a subset yet? What choices do I have for the third spot? Which ones? Okay, true or false? Now, do I have a full solution here? I do. right? Because I've now filled in all spots in my array, okay? And I have constructed the subset 1, 2, and 3. Does everybody kind of see that? Now, what do? I go back and say, is there any other choice for the last value? Well, I haven't yet put my F in here. And I now move forward. Is this a solution? Do I now have a subset? I have a fully filled out array, right? My next one I constructed was a 1, 2. Do I have any choices for the third position that I haven't used yet? This works better when people are yelling at me, okay? Is there any other choices for the third position? No, and it works better if people yell with the mics on, okay? Okay, so what do I got to do? I backtrack to this thing. My F hasn't been used. Now I've got a true and an F. What are my choices for the third position? What are my choices?
True or false?
True or false? Let's say I put a true in there. Okay. Do I now have a solution?
Yes.
And what is that solution?
1, 3.
1, 3. Bingo. And now do I have any other choices for the fourth position? For the third position? I put it through in there. I still have a false here, right? Do I have a solution?
Yes.
What is the solution?
1.
Now, do I have any other choices I haven't used for my third spot? Are there any choices I haven't used for my third spot?
No.
Are there any other choices I haven't used for my second spot? No. Are there any other choices I haven't used for my first spot?
Yes.
The answer is yes. I haven't used the F here yet. So let me put my F in here and now keep going. What choices do I have for the next spot? What are my choices?
True or false?
True or false? And when I pay, and what do I put down? I'm going to put down a true. What are my choices for the next spot? For the third spot, what are my choices?
True or false?
True or false? I'm going to put down a true. Do I now have a solution? I have a solution. Which solution is it? 2, 3. I now cycle through the other one. Do I have a solution? Which one is it? It is 2. Okay. Do I have any more choices for the second position? No. Do I have any more choices for the for the third position? I have no choices. For the second position, I do. My last thing now, I have a true or a false. I put down a true. Do I have a solution? It's an FFT. Yes, that is number 3. I replaced this. I got an FFF. What is my solution? It's the empty set. I have no more choices here. I have no more choices here. I have no more choices here. I back up. Does everybody see how I systematically constructed all subsets this way? Okay. Fair enough. What is my code? Okay. I showed you my backtrack routine. What is a solution? Is K equal to N? If N is the size of my array, if N is the number of the size of the subset elements that I want to build, what is the what you call it? Have I filled all K slots in my all N slots in my array? What are my choices for the kth position? Well, they are either true or they're false, so I've got 2 candidates. And this is what I'm returning. And the final thing that was actually the hardest of this in constructing subsets, if I want to print out my subsets like this, Okay, what am I now going to do? I'm going to go through my solution vector, which is a true-false thing. If a sub I is true, I'm going to print I. Okay, and done this way, I'm going to print out 1, 3, 4. Okay, if my solution vector was true, false, true, true, false. Okay, any questions about that? Do people see how backtracking had 3 slots unfilled? The 3 routines unfilled, they were is a solution, construct candidates, and process solution. And that's what I did here. Any questions how you construct all subsets of n things? Okay, backtracking will efficiently construct all subsets of n things. Any questions? Okay. And of course, you need to call it. This is what you do. You were originally doing backtracking where you're looking to fill an array A with n things. So far, you filled in 0 of them. Any questions? Okay, good. Now let's look at one other application of backtracking, which should be near to your heart because it's what you're going to do for your homework 4, essentially. Okay, at least somewhat, partially, kinda. Okay, is construct all permutations. How many permutations are there of the numbers 1, 2, 3? How many different arrangements are there of 3 things? Does anyone know? Okay, I'm hearing 6. Okay. In general, how many permutations are there of n things? Okay. How many things? N factorial. Why is that? Well, one way to think of it is I've got 3 choices for my first one. It could be a 1, a 2, or a 3. Once I fix that, I've got 2 numbers left for the second spot. I could choose either of them. And then 1 number for the third slot. 3 times 2 times 1. That's where the n factorial comes from, right? Okay. So what are we going to do? I want to construct all permutations in my array A. What do you think I should store in the ith element of my array if I'm representing a permutation? If I want to store permutations and represent a permutation, I claim a permutation of the numbers 1 through n should be an array with n elements in it, right? Where the number I put in the ith position is going to be the ith element of my permutation. Does everybody kind of see that? Could be 6, 1, 4. Let's say in this case, n was what? 1, 2, 3, 4, 5, 6, 7. N was equal to 7. What choices do I have for this spot if I want to make a permutation, for the next spot in my permutation? What possible numbers could be in that next spot? I started it with 6, 1, 4, 3. What are my choices for that? I'm hearing it could be a 2, a 5, and a 7. Namely, out of all the numbers from 1 to n, which ones haven't I used so far? That's what this is telling me, right? Those are my candidates for the next spot. Okay. So how can I use my backtracking to do this? Okay. I am going to set up my array. Let's go through and iterate through this. What are my choices for the first spot if I want to do n equals 3? What are my choices for the first spot in my permutation? What are my choices? Somebody. What possibilities could go in the first spot?
1, 2, or 3.
1, 2, 3. I put in a 1. What are my choices for the second spot?
2 or 3.
2 or 3. And I've dealt with this guy, right? What are my choices for the third spot?
Just 3.
3. Have I filled it in completely? Bingo. I now can print it out. That's 1, 2, 3. Do I have any other choices for the third spot? Do I have any other choices for the second spot? The answer is yes. I can put in a 3 now. And what other choices do I now have for the third spot?
2.
2. Is that an answer? Indeed, that's my permutation. Do I have any other choices for the third position? Do I have any other choices for the second position? No. Do I have any other choices for the first position? I can put in a 2. If I do that, what are my choices now for the second position?
1 or 3.
1 or 3. If I put in a 1, what are my choices for the third position?
3.
3. And ding, 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 I have a solution. Do I have any other choices for the third position? No. Do I have any other choices for the second position? I still could put in a 3 here, right? If I put in a 3, what are my choices for the first position, for the third position? Bingo, I got that. Are there any other choices for the last position? Any other choices for the next to last position? Any other choices for the first position? I still could start with a 3. If I do, what are my choices for the second position? What are my choices?
1 or 2.
1 or 2, and I'm going to put in a 1. Once I put in a 1, what are my choices for the third position? 2. 3, 1, 2, right? Any other choice for the second position? For the last position? Any other choice for the second position? Yeah, I could put in a 2. If I put in a 2, what are my choices for the last position? 1, 3, 2, 1. I've got no choices for the second position. I've got no choices for the last position, no choices for the second position, no choices for the first position. I am now done and I have generated all permutations. Any questions? I encourage you to go through these examples. Look at this backtrack tree that I created. See where it came from. Realize how the recursion is going. The recursion is going just like depth first search. Bunk, 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 bunk. That's exactly what's happening, right? Because backtracking really is like depth first search. Any questions? Okay, so I want you guys to understand how to construct all permutations. My code is pretty simple, actually. This is just basically saying fill the array with all the numbers from 1 to n that are not so far in the prefix. Originally, none of the numbers are available. Then none of the numbers are in the permutation. In perm is this thing. Then I'm going to go through my prefix and put down which numbers are in the permutation. And then my candidates, I will be a candidate for the ith slot, okay, or I will be a candidate for the kth slot if it is not yet in the permutation. And then I put it in there. So this is how I'm constructing all candidates. To process the solution, all I'm doing is printing out the permutation. And to tell I've got a solution, all I've got to do is fill it up. Any questions? If you understand how to generate all permutations, you will be a good person for the next homework. which is the famous backtracking contest algorithm program, homework. So homework 4, this one you do not work with a partner. This one you work individually. Your goal is to write a program to solve the backtracking, the bandwidth problem. What is the bandwidth problem? The input is a graph, and the output is a permutation of the vertices such that no edge is too long, that we minimize the length of the longest edge. What do I mean by this? Okay, look at this, at this particular ordering of this graph. What color is the longest edge of that graph?
Red.
The red one, right? From 1 to 8. That is 1, 2, 3, 4, 5, 6, 7 long. But what if I permute the vertices on the line? If you notice, this graph here is really a path. It goes from 1 to 8, to 8 to 2, 2 to 7, 7 to 3, 3 to 6, 6 to 4, 4 to 5. If I reorder the vertices, what is the length of the longest, with this layout of the vertices, what's the length of the longest edge? Does everybody see that every edge is actually as small as it possibly could be? It goes to its neighboring thing, right? This was a bad solution to the bandwidth problem. This is a great solution. What we seek to do is to find a permutation of the vertices such that we minimize the length of the longest edge. Okay? That is the bandwidth problem. Any questions about what the bandwidth problem is? Can anyone give me an algorithm to solve the bandwidth problem? Find the best possible permutation for any given graph.
Well, we could use an algorithm maybe similar to the problem before when we turned the graph into like 4 separate graphs and then used Dijkstra's algorithm.
Okay, you're getting a little bit fancy. The answer is I don't know how to do that. Okay, and I will tell you that there is no fast way to do this problem. Okay, so if you told me, oh, I've got an n² algorithm for this problem, or I've got an n³ algorithm for it, I'll tell you, you've got a wrong algorithm. Okay, how would we solve this problem? Can anyone give me a direct way to find the best permutation?
I mean, if you have n dots, then in order to guarantee a solution, wouldn't you just go through all 2 to the n, n factorial permutations, and then
Does everybody see, if I go through all n factorial permutations, if I constructed one after the other, and then took the graph and said, what is the longest edge with this permutation? That would give me an algorithm that is something like n factorial times m, okay? If you use even a simply reasonable algorithm. Construct all permutations, and for each one, check the edges against that permutation and tell me which one is longest. Okay? Any questions about that? Okay? So your goal now is, given a graph, okay, find the permutation which lays it out with the with the shortest, by minimizing the longest edge. Okay, and we are going to have the backtracking contest. That's not the problem for this year. This year it's bandwidth. Your job is, each one of you has to write an algorithm, implement it to solve the bandwidth problem. Read a graph in, okay, and return a permutation which has the minimum edge length for that graph. Okay. you will be graded on how fast your program is. The fastest program of all the student programs is going to be the winner of this of the contest, and they will receive a badge of honor. Okay? The slowest program will also receive a prize, but you don't want that prize. Okay? Any questions?
We can use any programming language, right?
You can use any programming language. Some of you guys are saying, I know C. C is a fast programming language. I'm not going to use something slow like Python. And I'm going to tell you, it doesn't matter what programming language you use, okay? Because this is going to be this is going to be one where the fastest program is going to be millions of times slower than you know, a typical program in here, okay? And it's going to be the one that does the backtracking in a way that it does the least amount of work, okay? C language might be 10 times faster than Python. I don't know, okay? Is 10 times matter? Or does making your thing so that you throw out a million, you use only explore 1/1,000,000th of as many permutations as the other guy? I'm going to argue that in this case, okay, you can use any language because you should use what language you're most familiar with, okay? The goal here is to come up with one that does as little search as possible, okay? And we will be talked about that. And you will be graded on your running time, okay? Or to be precise, what is the way I'm going to do this is I give you many different program data files. I recommend you run your program on the slowest data, on the smallest data file first, and wait a minute. Hopefully you've got an answer then. If so, you can go to a bigger data file. I'm not even going to want to know the running time of your program. That doesn't interest me. I want to know what is the largest example you can do. Because what I expect your program's going to do, you're going to run your program on the smallest file. And you say, hey, it gives me the answer right away. And you'll run it on the next biggest. And you'll say, hey, it gives me the answer right away. And you'll run it on the next biggest, and it goes into outer space and never comes back. Okay? I want to know what is the biggest file that you guys are capable of solving in 1 minute of waiting on your computer in your favorite programming language. Okay? Any questions about that? That is the backtrack challenge. Okay? Some of you may say, I got a faster computer. Okay? My daddy has a real fast computer. I'm going to run it on that machine. And if so, that's fine. That computer is only 10 times faster than the guy whose computer he bought, you know, who's got the worst computer in the class. Being 10 times faster isn't going to make much of a difference. You want to be millions of times faster in order to win the contest. Okay? And I'm going to be wanting you, okay, I may change my the input procedures a little bit, but basically your job is to write the fastest program for solving my backtracking thing. Okay, any questions about that? So I want you to read, for next class, read the assignment, okay? Make sure you understand backtracking. Ideally, write a simple, stupid implementation. Namely, as I said, construct all permutations. Find the edge that is biggest for that permutation. Find the permutation that has the smallest, biggest edge. Okay? If you do it that way, okay, it will be, this is not going to be that hard a program, but that will be slow. Next class, we're going to talk more about how do we make it faster, okay? But I strongly encourage people to do the dumb, simple thing first, okay? And then we can worry about speeding it up. Any questions? Any questions at all? Okay, so think about it, start looking at it, and we will discuss this again next class, okay?